All right, we'll go ahead and get started. Good afternoon or morning, depending on where you are today. Hello, everyone. Welcome to the Adaptive Route Optimization Concept of Operations and System Requirements Specification webinar. My name is Luana Brashears, and I'll be helping with facilitating today's webinar. This webinar is part of the Roadways webinar series sponsored by the Federal Highway Administration. Just as a quick reminder, if you don't know already, at NOCO, we offer a variety of resources to support the transportation system management operations community. You can go to the NOCO's website and you can browse through links for TISMO resources and news. Also, previous webinar recordings and case studies can be accessed from there. And just a few logistics for today's webinar. We're recording this webinar, and this recorded will be available on the NOCO's website as well, probably next week. All of you are encouraged to stay engaged by using the Q&A feature for questions. So if you look, there's a Q&A feature in the bottom of your screen. So if you have any questions at any time, feel free to add those questions to the Q&A pod. And also, if you have any comments, feel free to add those to the chat feature. So if you have anything that's not a question, if you have any comments, use the chat feature for that also in the bottom of your screen. Our Q&A session will be at the end of all presentations. So if you have any questions at any time, just enter them in the Q&A area as they come to your mind. Also, feel free to say hi to your peers, enter your name and agency in the chat to say hello. And just to give you a disclaimer for this presentation, product names may be used during the webinar, but the U.S. government does not endorse any product. Additionally, views and opinions expressed in this presentation are the presenters, and they do not necessarily reflect those of the Federal Highway Administration. And now I'll hand it over to David Johnson from FHWA. He will be today's webinar moderator.
Thanks, Luana, and thanks to everybody for joining today. I appreciate it. I was just on a virtual work zone conference, so if anybody was taking the time to attend that and came over here, I appreciate it. I think I see a few names. So I wanted to, first of all, thank NOCO for supporting our road weather management spotlight series, Luana and Adam in particular for continuing to host these. This is our, I believe, fifth spotlight webinar, and we will continue next month. We have another research update on our IMRCP project, so please stay tuned for our invitations on that. But for this one, we want to talk about our work on adaptive route optimization and our concept of operations and system requirement specification work and the research that we have going on there. Again, I just want to thank everybody for joining. We do have quite a bit to cover, so I'm not going to delay the introductions any more than I have to. So I'm going to hand it over to Neil Hawkins. Neil is the Associate Director at the Institute for Transportation at Iowa State University. And Kyle Garrett, who will be the Principal Researcher for ARO from Synesis Partners. They're working as a sub under the Leidos for this project. So with that, I will hand it over to Neil and Kyle, and they will go through some of the research findings and talk through the project. Neil, Kyle, the floor is yours.
Great. Thanks, David. Thanks, Luana. Appreciate everybody jumping on this webinar today. Luana, if you would go ahead and advance the slide. So I'm going to give you a brief introduction into adaptive route optimization. You're going to hear us refer to it as ARO at some point. You'll probably hear us refer to it as ARO. So just ride along with us on that. But we're really talking to you about a concept of operations that was developed as well as system requirement specification. Kyle will be going over those next. Go ahead, Luana. So let's start with just some perspective. Many of you on the call don't need to be reminded that there are over 200,000 injuries, 4,000 fatalities on our roads due to adverse weather every year. And specific to winter conditions, state DOTs alone spend about $2 billion per year on snow and ice control, and another $5 billion fixing the infrastructure and repairing it due to chemical use, degradation, and operations. Go ahead, Luana. Research has shown that when we can provide more timely, accurate, and route-based condition information, we're going to reduce winter winter weather-related crashes, injuries, and fatals on the highway network, because we simply change the driver's behavior by providing that information. And so that it helps agency staff determining how and when to combat storms, which routes to hit. And so it's really important that we focus on our route and our effectiveness of those routes and how we communicate that. Go ahead, Luana. So winter maintenance requires a lot of resources in very short bursts of time. And your agency capabilities are regularly challenged in the areas of treatment capacity, how much of the fleet's available, how much materials available, in terms of staffing, who showed up, who is available for any given storm, and the weather, the timing of the weather, the intensity, the forecast, and so overall for safety and agency efficiency, these things are impacted in how you can fight a storm and how variable they are. So our static routing plans based on historic conditions, they lose efficiency over time, and they don't adapt to changing in weather conditions, changing in staff, and changing in your capacity for each storm to fight it. Go ahead. So lastly, we know that each agency has your own goals. You have your own challenges in getting back to pre-storm levels of service. And then those results for a specific segment of road depend on a lot of factors: type of storm, precip, the timing, how well you were able to get out and do any pre-storm operations, what kind of travel conditions. Is it at 4 o'clock in the afternoon near downtown, or is it late at night on a weekend? And the type of treatments available due to weather. And then also that the snowplow routing can be awfully complex. And there's no question that improved efficiency in the routing alone would lead to safety for motorists, your crew, and your agency resources. Go ahead. So let's take just a minute and ask, what is adaptive route optimization? More specifically, it's a method of dynamically and effectively routing winter maintenance vehicles across all segments of your network to meet your maintenance objectives, your service goals. And the term adaptive really refers to the optimal path being selected, even when routing priorities change or failures occur along a route, like incidents, severe weather, emergency road repairs, road closures, things like that. Go ahead. Specific to ARO, it uses real-time and historic data to dynamically change and adapt to your winter operations, your plow routes, based again on these changing conditions, and who hasn't experienced changes in staffing, equipment, and material resources on a storm-by-storm basis. We live in Iowa, where I'm at. We've had 2 derechos since 2020. And when we first saw the word derecho, we all said, what is a derecho? So things have changed, and the intensity of weather is definitely changing. Go ahead. This project had some challenges that we were trying to develop a tool that would also need some access to additional data. So that's a challenge for you as an agency. Accessing that requires some homework. How would you get that kind of information and integrate it in with your decision making? And you all have different routing needs. You have varied traffic and climate conditions and road characteristics and service goals. So when we put a concept of operations together and a user requirements together, that was a noteworthy challenge for sure. This graphic sort of walks you through an adaptive route optimization process, starting with an adaptive route on the far left, say 9 o'clock, but really beginning with every storm with the available resources. What do you have available in terms of equipment, material, and staff to fight that storm? What are the service goals that you have? What kind of weather hit you or is going to hit? What kind of road closures or congestion are you facing? And then we also have incorporated snowplow operator feedback in that process to continually adapt the routes, just like all of the package delivery that happens on our roads and to our houses every day. Go ahead. So we included a lot of stakeholder input. And so from left to right, this is sort of the process we went through. We looked at the literature, we spoke with a lot of agencies. We then developed the concept of operations and systems requirements that Kyle will touch on. With that, Kyle, I'll turn it over to you.
Thank you, Neil. Let's go to the next slide if we can. So we're going to talk about the concept of operations. And to some folks, I suppose that's an intimidating kind of thing, but it's actually pretty straightforward. We're going to walk through that. Luana, next one, please. The real purpose of a concept of operations, of course, is based on the stakeholder input to document the user needs. And going with that, the expectations, what the goals for the system, in this case, the aero system would be. It has to characterize what everybody has in their head. What, in this case, would aero look like? And it has to do that for all of the stakeholders that are involved. In this case, it could be the operators, sitting back in a TMC. It could be the, the drivers out on the road. Next, please. So we're going to walk through it has to, first of all, capture those user needs, the expectations and the objectives. It has to describe them all in enough detail that all of the stakeholders then see their role in it, see their input, see what came from that. All that information then serves to provide a bridge from the problems and the user needs that we defined up front to what the system could actually look like, and eventually to the system level requirements that we'll be talking about next. So a concept of operations is pretty a standard document. It's defined by a set of chapters that really walk you through the process of, what's the background, what's the purpose of it, what's the current state, in our case for winter operations, what things need to change, what is it we're really trying to accomplish by building an aero system. It then has to describe those concepts in some detail, at least enough that we can go on to talk about how it's going to work in the future. It has to identify and describe the use cases. In other words, we've got this great idea, but how are people in practice going to use it? It has to describe the potential impacts of it. If it were used, what difference would it actually make? What kinds of things would have to change in an agency in order to make it work? And then lastly, we want to hit what we usually just call the analysis, all the potential advantages, the opportunities, sometimes disadvantages, and the risks in doing that deployment. And then of course, then there's a reference section that tries to provide enough background for how that would all work. So let's take a look at today and what goes on with respect to routing. And this is just typical. This is the big picture. Your agency may look a little different in the way that it does things. So the people on the outside are the users, if you will, and each one of the ellipses going down the middle are effectively the use cases. So beginning at the top, winter maintenance starts with, before the season comes in, with setting maintenance objectives. You then have to align all of the resources that you need, the human, capital, material resources, drivers, trucks, materials, and all of that has to be brought together so that you have it when the season sets in. And then as each storm comes in, we have to monitor weather conditions. That can get pretty complicated, of course. In a lot of cases, we want to be monitoring traffic as well to make sure that maybe we have some service level objectives for the traffic itself that we want to maintain. We have to assess the pavement conditions as we go along. Some of you actually have information coming back from your plow trucks as to pavement condition. Well, that needs to be brought in as well. We have to plan the routes to begin with, and those are usually fixed or static. And then of course, a plow truck driver, has to actually be out there doing that. Routing addresses all of those things together. All right. The current state tries to pull together then, here's a view of all of the components that interact to make it work. They're shown here. The following concepts they're common to most winter maintenance activities. We have staff representing the human resources. We have a fleet of vehicles. We have a road network that the vehicles have to operate on top of. We have weather forecasts. We have routing plans in most cases in today's current state. Those are fixed or they're static. They don't change. It's just a question of when we start them and how often we cycle. We have a treatment plan that goes with that. You may have pavement forecasts that might be helpful. We generally, or almost always, will have some sort of environmental sensor stations and road weather information systems that may be feeding into that as well. The road segments themselves, of course, are the things that get treated. They're the things that collectively make the road network. A route is just a collection of those along which the winter maintenance will occur. A shed, as you all know better even than I certainly do, it's just the place, a facility from which the drivers are starting and stopping. Depots are a little different than that in the sense that they contain material. I may not be starting there. They could be out somewhere in the field and I'm simply stopping by to get more material during my route. And then a maintenance shed itself can support either fuel or material. Next slide, please. So having talked about all of the field stuff, effectively, the layout of how everything's put together, we want to talk specifically about the truck, which is a big part of the routing. Current configurations include one or more plow blades along with equipment to distribute the solid and liquid materials. As shown here, the truck may carry the following equipment and monitoring road conditions and maintenance operations. So it has a plow. It has or may have a spreader and a sprayer. It may have an automated vehicle location system and a driver interface in the cab for sending information back to a maintenance management system. And it may have sensors for integrated mobile observations. In other words, for ESS that's mounted on the truck itself. To talk about the routes themselves, route optimization, as I think Neil said, is a process for determining the most effective route that meets the service objectives that are set generally at the beginning of the season. It's generally considered static, meaning that routes don't change without manual intervention once the process has been applied. The fixed routes are based on expected conditions. So it could be on storm intensity, traffic patterns, truck availability, and traffic conditions. It doesn't account for extreme weather events, in other words, unexpected kinds of conditions, or unexpected issues that may come up during the storm. It is an advancement over the simple, shortest route kind of planning, but it's still not really necessarily adaptive. Next one, please. So we want to talk a little bit about the stakeholders. I think I listed them or showed them to you on a prior slide, but for the purposes of defining what the current state looks like, we grouped everybody this way. So we have to have some operations and maintenance management, typically higher up in the agency, that are really setting the objectives. They have a perspective that goes across the entire area of operations and road network. They're going to coordinate activities and resources across districts and within their own agencies, and sometimes even with other agencies. Maybe it's across state lines. A district maintenance manager engineer, typically looking at it a level down from that. They're perhaps less concerned with setting objectives and more with how are we going to meet those objectives. They're going to coordinate as the higher level management may with other agencies, making sure the public gets served across urban and rural settings, across all the roadway functional classifications, and even across jurisdictional boundaries. The supervisors, the guys typically out in the sheds that are overseeing activities for that area, they monitor the weather conditions, traffic conditions, timing of operations. They may be out in their own truck monitoring pavement conditions. And then, of course, once the storm starts up, they're generally one of those that are managing and overseeing all the communications with the drivers as the routes get driven. They also have to manage and monitor the resources at the maintenance facilities. They have to work with the district managers to ensure that their staffing and vehicles and materials are busy guys. Traffic management supervisors and operators may also be involved. They can support those operations. They may receive, for example, near real-time reports of conditions. They may be getting that through, for example, a 511 system or 911 phone calls. They may be working with emergency dispatch, and they try to make sure that that all gets passed back and forth with the maintenance supervisors. We talked a little bit about the routing analysts. They may assist the maintenance supervisors in getting things going and setting up the routes. Most of the folks in the current state, at least, are using static routes. These come from years of practice. They probably come from, somebody who drove routes for, 10, 15, 20 years in that area. The routing analyst role, because most agencies are not going to have somebody with that title, could be filled by a maintenance supervisor, could be a contractor, but in some cases, they're brought specifically in to recommend route improvements. And last, but certainly not least, the drivers are the on-the-ground implementers of the routing plan. They get the routing and treatment plans at the start of the maintenance cycle. They make real-time routing decisions based on what they're seeing out on the road. They have to communicate with the supervisors to work around situations that come up. And then they have to submit their reports at the end of the shift. It's important to understand here that when in the current state, at least, we're talking about different modes of operation for routing. So they could be static routing, optimized static routing, and adaptive or in-route routing. As things stand today, static routing is when the routes are based on available maintenance vehicles and facilities in the service area. They typically don't change, and that's what most agencies are using. Optimized static routing means that some analyst has gone through and based upon one or more constraints said, this is probably the best set of routes that we can come up with to meet those criteria. So it'd only be revised generally when you have big changes in the road network, in the performance criteria for the routing, or the optimization parameters have changed. Adaptive routing today probably doesn't happen much in a central office or even in a maintenance shed, but it does frequently happen out on the road. A driver might become aware of changing circumstances like an incident that require rerouting, then they have to notify the maintenance supervisor of the change plan. It could be a changed weather forecast, and a route might simply be canceled, or it might go to a longer cycle time. New routes are adapted to the immediate circumstances rather than changed intentionally. All right. So we want to talk about concepts now. We've kind of built up all of the background for the current state. We want to talk about what the future state looks like. So we're going to talk specifically here about what's changed, not go through every little icon on this diagram. One thing you'll notice is we have an orange line around virtually everything. If we're going to do if we're going to do adaptive route optimization, we really have to have all of these functions involved. Nothing's going to get left out. The plan route is changed. We effectively don't have a routing analyst. That's all goes into what the system is going to do. And down towards the second one from the bottom, it simply says optimized adaptive route. Next one, please. We looked at this before, and you'll see it's changed too. We now have something called a routing service. That replaces the routing plan. It dynamically provides optimized route plans adapted to the current conditions. The pavement forecast is no longer an optional component. It actually becomes a primary component of an adaptive optimized solution. We have to have information on what pavement conditions are likely to look like in order to do adaptive routing. And then, of course, we have changes on the truck as well, on the plow truck. So for adaptive routing, we have to have AVL. We have to have that automated vehicle location information so that we know where the trucks are and what the route status looks like. We also have to have a driver interface because we may be updating the routes and we may be providing turn-by-turn recommendations to the drivers for what those adaptive routes now are going to look like. So here's a view of everything that has to come together into the routing service to make this work. There are a lot of data sources and interfaces to support its use cases. First, we have to have a road network model. That means that it's a live information-based system. It has to include all the segments to be treated and plowed, all of the routable connections between those segments. The connections have to include movements through intersections. So we have to know whether it can be through travel, left, right, U-turns. If there are crossovers through medians, those need to be included on the maps, and even turnarounds at the end of a route or at a cul-de-sac. Service objectives. We have to have service objectives, whether it's for a set of segments, maybe it's by district, maybe it's by road classifications, but those objectives enable managers to specify things like maximum time to clearance or pavement state goals, minimum cycle times, other criteria that they may come up with. We have to have material, staff, and equipment resources. They have to be allocated to the routing service or by the routing service as they may be needed to meet the objectives. The interfaces for that might be provided by an enterprise resource planning system. It could be defined by a maintenance supervisor or an asset management system. It could even be through an aero-specific interface. In other words, it's just a screen where we say these people are available, these plow trucks are available, that kind of thing. And we have to have traffic data and timely notifications of incidents. They're probably going to come from a third-party interface, or it could come from an ATMS, but it does have to be real time. We have to have weather information for Aero. We have to have all the atmospheric weather data, the pavement conditions forecast from somewhere to go into the treatment plans. We have to have AVL data. We have to have the adaptive routes themselves. And then there has to be a route management dashboard to provide performance metrics for the routing functions. Wow, a lot on that chart. Next slide, please. Okay, so we want to talk quickly about operational scenarios. If I build out the system and if I have all of those resources, what can I do about it? So the ConOps describes 3 scenarios that highlight particular sets of those interfaces and functions and how they all work together. The first scenario that was identified had to do with shifting resources. Given that an aero system needs, that it then needs to be able to optimize the snowplow routes. In this scenario, for example, a metro area might be hit by a storm that a rural area is not seeing. So the aero system then would, based on that weather forecast and traffic conditions, show that the service goals might not be met for that urban area. It would then want to shift resources from the rural to the urban area to try and make up the difference. And we have to rerun that optimization with those additional plows and personnel shifted to the metro area from those bordering areas. And then the results from the revised analysis would show that the metro area met their service goals. The next scenario has to do with changing weather forecasts. Maybe the weather forecast is solid, but it's just changing over time. The aero system needs to keep up with those changing forecasts, even though the precip amounts and the types from winter storms, we know that's difficult to do. So in this example, heavy snow forecasted ends up producing only freezing rain, for example. The aero system has to reassess the optimal routings based on that. We're going to be doing more pre-treatment and than plowing. The new route instructions have to be sent to the trucks and drivers, and the resulting routes are going to reduce the returns to the depot because I'm not putting down as much salt, say, and the first cycle treatment. Next. And then the third scenario that we included in the ConOps has to do with an incident occurring en route. Incidents are not infrequent on snowplow routes. They can slow the storm response. So the system needs to tactically then re-optimize around those events. So in this example, a snowplow operator is following prescribed patrol route. Crash occurs on an untreated section of roadway, we'll say 3 miles ahead of the driver, prevents the road from being plowed while that incident's being cleared. So the system needs to then reroute that to continue plow operations rather than have the plow operator just sit there. The TMC operators can observe that incident, log the location, the lane's closed, and give that information, put that information into an ATMS. Then the Aero system would then recompute the plow's route with others in the area based upon the clearance time for the incident, based on the weather conditions, based on how many material resources they might have, maybe even on the presence of a queue building up from the incident. It then has to send those new routing plans to the trucks in the field, and for that matter, to the other trucks in the area that might be affected by that incident. All right, that pretty much packages up the ConOps. We want to go from there into a discussion of requirements. And this is really requirements for the system itself. So let's dive into that and see what it looks like. As a reminder, a system requirements specification, if written well, describes what the system will do, but it doesn't describe how it's going to do it. That's part of the system design that comes later. It more formally, if you really want to say it right, it defines the high-level system requirements that cover the entire domain that it has to be operated within. That's why we specify scenarios, along with all of the background information about the objectives. It describes the target environment. It may even describe constraints and assumptions and non-functional requirements that affect the system. There are standards for how these kinds of documents get written. In this case, it comes from the IEEE Systems and Software Engineering Lifecycle Processes Requirements document. The purpose of this requirement specification is to provide an adaptive snowplow routing optimization solution for DOT maintenance and operations personnel to use during adverse weather. It supports improving both the safety and mobility of all roads through adaptable and optimized snowplow routing. The scope of this then incorporates real-time and historic data in snowplow routing solutions and supports both a strategic view, in other words, for planning, and a tactical view for real-time operations. It describes dashboards and feedback opportunities for the users, including managers and the supervisors and the drivers. So given that this specification describes what the system will do, when it's implemented, it has to have some context. It has to have input on what the future system should do. That, for the most part, then came out of the survey that Neil talked about. It comes from a definition of the needs, which is based upon the concept of operations, and then an analysis of the requirements that flow down from those needs and from the concept that we packaged up in the concept of operations. These are high-level functional capabilities. The system functions reflect the desired characteristics in terms of user needs and system attributes, system constraints. To simplify all of that, each user need gets numbered. In this case, there were 30 of them. And that's regardless of what kind of need it was, whether it was a formal functional need, whether it was an attribute of the system itself or a constraint. Next slide describes this a little bit more clearly. So functional needs are those things that the system needs to do or enable users to do. So for example, For Arrow, the system needs to enable maintenance managers to set maintenance operations objectives like level of service and cycle time. Or the system needs to monitor atmospheric weather conditions like precipitation type and rates and temperatures. It needs that because that's part of the basis for doing the route optimization. There are also interface needs. Those describe the means by which the system exchanges information with its users. So for example, for Arrow, the system needs a means of specifying those maintenance objectives that we talked about before. And it needs a means of specifying how big the road network is and which segments on it which need to be routed. There are performance needs. This defines the limitations or constraints on the system and how it has to operate itself. So a big one for an Arrow system is the system needs to provide optimized routes fast enough that they can actually be implemented in route. In other words, there's no point in doing a route optimization if it's going to take 4 hours to run that calculation and the route cycle time is only 2 hours. There are also non-functional needs. So these are the more general things that have to happen in order for the system to be implemented and run reliably. So it could be something like, literally, the system needs to be reliable, or it needs to implement open data specifications to the extent that they exist, maybe so that it can communicate with other data systems. System attributes describe things that the system has to do or look like. So for an Arrow system, it may need to have secure communications between the operation centers and the maintenance vehicles. Or it may need to have sufficient computing power to meet the performance needs, right? I can, if I'm worried about how long it takes for the computations to run, I just need maybe a bigger box to run them. Constraints define the limitations on the system or its operations by the users or other systems. For example, for Snowplow route optimization, the system needs its driver interfaces to comply with agency policies for in-vehicle use. If the agency policy is that the system, that a driver is not supposed to be using a touchscreen keypad or keypad over on the side, then the system is going to have to be designed to not require the driver to do that. All right, so the first part then of the system requirements then provides a table of expectations, not so much user needs, but expectations for how Arrow is going to work. So in this particular case, we build a table that has changing conditions in the left-hand column. So these are grouped by agency objectives or resources or weather and road conditions. And then we have divided it into things that have to be worked on strategically before the vehicles actually go into the field, or tactically why everything's en route. So for example, if you have a driver shortage, you might want to expect the Arrow system to support that by both strategically and tactically, to optimize the agency resources, to make sure that the routes are actually drivable with the number of drivers that we have. Next slide, please. Okay, it's an awful lot of information now. So in order to make it usable, we have to organize it. So the system is built around a set of tables that compile all of the functional requirements. The first one, the first column identifies a category and a number and a requirement type. The second column shows the system requirements, describes what the system is actually supposed to do or how it's going to behave. The third column includes notes. Maybe there needs to be a basis for that or just an explanation of what it actually means in practice. And then the fourth column relates to where did this come from? Did it come directly from a user need, or is maybe this associated with a higher level requirement? So now we want to talk about the types of, or the way that all of these got captured. The requirement types on the left We're going to get to that in the next slide, but we essentially had to compile this into, believe it or not, 16 different tables that are grouped functionally. Requirement types. All right, so we've talked about functional and interface, and I think to some extent performance. Those are the ones that talk about capacity or speed, measurable criteria applied to the system. But there can also be security requirements, how the interfacing systems and users access the system. There are going to be data requirements. In other words, how does the data that the system needs get accessed or stored, or for that matter, even delivered? And then there have to be reliability requirements, a criteria for availability and up and down time, failure and recovery, maybe related to the other performance criteria. I want to walk really quickly through then some of these, the categories, managing maintenance objectives, maintenance resources. There are some monitoring requirements around weather conditions and road weather conditions. We have to be able to manage the treatment plans themselves, while all the while monitoring traffic conditions. There's maintenance vehicle operations and monitoring those, managing road network configurations, maintenance routes, optimizing the routes. How does that actually work? Defining requirements for that. And then once we have those routes generated, how do we provide them to people? There are performance indicators. We know that generally these things look best on a map. So there's requirements for what a map-based presentation or user interface would look like. We're going to want reports on the routing and the performance of the optimization. So we're going to have that. And then there'll be some general system requirements too. All right. The next chapter of the system requirements then defines the key assumptions and the related dependencies. For example, the aero system will need detailed maps on which to base its optimized routes. Maintenance vehicles may use roadways and parking surfaces that aren't normally indicated on navigation maps. Things like a turnaround. Multi-lane roads will require a vehicle to pass along each lane. And generally maps don't include a breakdown of lanes if they're built for navigation. And it can vary from one segment to the next. So that kind of information has to get included. The aero system is going to need extensive data resources to optimize routes. If it can't get all of that data, it may compromise the accuracy or quality of the routing and limit its application. The aero system needs information on maintenance resources. So we have to have all of that in order to get the routing done. At a high level, then, implementation of aero requires things like a routable network, being able to define that and which segments the plow truck is going to pass over. We have to have information, or we have to have rather a plow truck fleet that does have AVL. We have to have driver interfaces in the vehicle, subject to the use constraints that the agency may put on those. And then we have to have a supervisor interface for monitoring that for management purposes. At the agency level, very specifically then, we have to have information on all the maintenance resources. We have to have vehicle locations en route. We have to have traffic conditions, probably from an ATMS or from a third-party data source. We have to have treatment plans, atmospheric weather conditions, and road weather conditions. All right. Wow. That's a lot, Neil. I'm going to pass it back to you for the summary.
Good job, Kyle. Appreciate it. You covered a lot of ground and a lot of lists, so thank you very much. We're just going to wrap this up. Luana, if you'd go ahead and advance to one more slide, please. One more. Thank you. This one. So we've talked about adaptive route optimization. We've shared this graphic where to achieve optimized routes as the entire package delivery world and other things have had to move to, it's really based on the fact that your resources are changing, your goals may change, your weather is definitely changing, and things happen as you are in this very intense period of cleaning up during and after winter storms, and even the work you do before. Go ahead. So with that in mind, we just want to list some of the potential benefits of an adaptive route optimization. It improves your agency response. It helps to optimize the routes with a reallocation of resources and the limitations that you face. It also considers the weather conditions that have actually hit you in lieu of the treatment cycles that you want to meet. And it helps you tactically re-optimize the route patrols, active incident sites, and all the things that are occurring during those times, hopefully to reduce deadhead, reduce total route miles, and save on materials. Go ahead. So in summary, it helps adapt to changing conditions, improve your winter maintenance and operational efficiencies. We've provided a concept of operations as well as a systems requirements document that are based on user input, that take those and put them into these requirements that Kyle just highlighted, and looking at incorporating real-time and historic data, providing strategic views of maintenance in terms of both planning and tactical for the real-time operations, including agency level goals, your routes and segment priorities, your cycle time expectations, the road conditions, other real-time inputs like atmospheric weather and road condition, surface condition, incidents, work zones, traffic volumes, and then considers risk. It can consider historical crash risk, recurring problem areas, and things like that. And then really help to improve operations through your vehicle location inputs, and also, as Kyle noted, dealing with the details of things like turnarounds, U-turns, different maneuvers that your trucks are making that aren't normal routable network instructions for most drivers, as well as minimizing deadhead. So although it can be complex, there's no question that as we focus and discuss how to improve routing efficiency based on all these things that change all the time, it could lead to improved safety for motorists and agency staff along the way. So with that, David, I think I'll turn it back over to you.
Thanks, Neil and Kyle. You guys went through that in record time, so I appreciate it. It looks like Scott just posted a question real quick. Let me see. Oh, we got a couple here. All right. In the chat, if you want to post your questions, now's your chance. I think Scott's came in first. So first question from Scott: has anyone implemented an adaptive route optimization program? If so, did they develop the program in-house or have it developed by a vendor? Kyle, you want to touch on kind of the interview process that we went through under one of the tasks on who you reached out to and what the responses were?
Oh boy, you're going to challenge my memory, David, to go back and who we specifically talked to. We did talk to a number of folks. We did a survey of an ad hoc survey of who has done some of this work. I think some of you may be aware that route optimization is not that uncommon. It happens pretty frequently as road networks change or as resources and new equipment becomes available. What's less likely is to find anybody, honestly, who's doing adaptive route optimization in real time. And my recollection, David, correct me if I'm wrong, was that nobody's actually doing that we know of, although a lot of folks have done studies similar to this to try and look at what might be required. I don't know, you or Neil have anything to add to that?
I'll just add that, Scott, we did a survey, as Kyle noted, but we then did agency interviews. We talked with 3 DOTs, North Dakota, Wisconsin, and Ohio. We also then talked with the city of West Des Moines, Iowa, as well as Pittsburgh, city of Pittsburgh, to get their input, their user needs, their thoughts on this as well. Obviously, we would have liked to have had more conversations. We also, in a literature review, we looked at a lot of the business literature on supply chain and how so many companies were forced to adapt during the pandemic, either sort of adapt or die. is the way that literature kind of summarizes it, and how so many of them realized they can't predict their demand and their ability to pivot, from traditional business to business to home deliveries and all that really relied on an adaptive tool. That's in the business world, not in the winter operations, but I just wanted to offer that as some of the reading and information we've reviewed putting this together.
Yep. Thanks, Neil and Kyle. Appreciate that. Let me go over to the Q&A real quick. Bob Hart, there are a number of latencies in the real-time data sources and data aggregation and processing. Thus, what do you see as the time frame of the optimization guidance? Anybody
Good
want
question, Bob. Good question. Well, we mentioned, I think, in the slides, one of the criteria that we have for the system is that it has to be able to produce its optimizations faster than the routes are being driven. No point in doing that if you can't get the updates out to folks before they have their routes completed. That's really challenging. I think for the most part, we're less worried about the latencies than we are actually about just the computational time to get everything done. The weather forecasts, of course, Bob, don't change that frequently. The sensed weather conditions do, but like any weather forecast, we'll take the data as it comes in with the intent of using the most recent data that are available. Traffic data is more frequent even than weather data, so that's pretty easy to cover, and there's not really that much latency associated with it. Throwing the data all together, again, that's pretty straightforward, but the latency and the computation itself is probably going to turn out to be the biggest constraint.
And Kyle, I remember some conversations that actual time might be dependent on a lowest common denominator for a specific agency among those sources. They may choose 1 hour is fine, or even 4 hours are fine for them, but that it's not prescribed. It has to be, every 1 minute or something to that degree. Exactly. Yep.
Yeah, we would see in Colorado, sometimes some of the more rural patrols would, they would have their, maintenance decision support system up in their tablet and their cabs, and they wouldn't be able to really submit reporting or anything until they got back to the shed, and then they had internet access closer to their facilities. And then they would, check to see what the latest recommendation and treatment recommendation would be while they were filling up at the facility, and then head back out and then come back in a couple hours and do the same thing again. They wouldn't necessarily have real-time data while they're on their route, but they would get some sort of data download and input from the system once they came back to connectivity areas like their facilities. Something like that could be similar in practice. Next question, and we're running out of time here, so I'm going to get through as many of these as I possibly can. Are there good examples of arrow in practice at specific DOTs? Kind of covered that already. I would say no, there are not good examples. There's been a few pilots here and there, but this is more looking at how to optimize something, a winter operation practice that's been going on for the, all intents and purposes very similarly for quite some time. So we're being asked, all of us with our workforce issues, how to do more with limited resources. So this is something to take a look at. And one of the things from this is the concept of operations and the system requirement documentation will be publicly available, hopefully in the next month or two, once it finishes going through the public affairs review process. At that point, we're going to be looking at, publicly having those on our website, and anyone would be available to go in and download those and look at the system requirements and ConOps and see if they fit for their specific needs. If they don't, they'd be welcome to make edits and build something out from those documents if that suits the agency's particular interests. Hazim said, number one, is an optimized route assigned to one truck or multiple trucks? It's probably going to depend on the route, Hazim. Some of the more rural areas, you only need one one truck to meet your levels of service needs. In a more urban setting, multiple trucks could be assigned to the same route. Number two, do the drivers go through a training? Very good question. Training obviously is going to be a massive lift. If ARO does become institutionalized on some level, or DOTs, agencies start using this, driver training is going to be probably one of the biggest hurdles and would necessitate its own, very similar to what MDSS was back in the day. It's a culture shift. So anything like that would obviously need some sort of heavy training support. If this is built out in the future, I would suspect something through NHI would be developed. That's my idea anyway. We'll see how it goes. And the last one from Hazim was there any study on the safety with the extra work assigned to drivers? I'm not really sure if you're referring to driver hours. I don't know if you have a follow-up on that, or if any panelist has some insight on that question.
He might be referring to the driver feedback, having a tablet in the truck, any kind of reaction. Is it a voice in the cab? What is being asked of the driver?
Yeah, that's really no different than what you'd see with MDSS and the cab of vehicles. It'd be a similar readout. You'd look at it. There should be some sort of probably voice feedback from the systems, very similar to GPS, where it tells you what your turn-by-turn instructions would be. All right, I got one more, and then I have a couple announcements from Mike. If ARO hasn't been done, what are the barriers? I think a lot of the barriers are data accessibility, latency is another one. Not all DOTs have AVL. We saw that AVL is a necessary component of this. So I think it's really maybe a little bit ahead of its time as far as our technology goes, but we're getting to that point. There are certainly DOTs out there that have all the pieces needed. They really just need an interface to start a pilot for this, I would say. So quite a few barriers for some DOTs, but maybe not so many right now for others. I apologize, Bob, you got one more question, but I got to close this off. I do have something in the chat that I want to post. These are the new SMART grants that the US DOT has just announced. The application period for these is open through, I believe, November 18th. If you go to that link and click on illustrative use cases, there's a lot of road weather management language, particularly with things like roadway flooding. There's also something about delivery and logistics, which I think has interesting ties to ARO. So I'd encourage everybody to take a look at that. There's, I believe, $100 million available for these SMART grants, and they do certainly have broad road weather management applications. So if you could, I think I sent that to the wrong person, actually. Give me 1 second here. Sorry. Send it to everybody, not just one person. There we go. So take a look at that when you get a chance. And then there is a link on there that says illustrative use cases. If that meets your particular agency's needs, by all means, feel free to ask me any questions or submit materials for that grant application. I believe that was it. Thank you for everything that for our speakers, Neil and Kyle, appreciate it. Again, a special thank you to NOCO for hosting us. And with that, I think I'll turn it over to Luana to close us out. Thanks.
Thank you, David, and thank you everyone for attending today's webinar. Thank you especially to our panelists. Great presentation today. We had a great discussion as well. As I mentioned in the beginning, a recorded version of this webinar will be available at the NOCO website. And on behalf of the National Operations Center of Excellence and all our presenters, thank you so much for joining us today, and have a great rest of your day. Bye.